Okay, hopefully I've fixed all the slides, so let's continue on. So state machine for multi-cycle, state 0 and state 1 is going to be the same for every instruction because we haven't figured out what instruction we're doing. C0 is to fetch the instruction, aka get it out of memory. Decode is to figure out what that instruction is, and then you transition to different states for every instruction. So in this architecture, we're going to keep it simple and it's 2 extra cycles for all instructions, except for a move L, which has that extra instruction because that's a load from memory and write to the register file. We'll go ahead and give these states, or these numbers. So we have our finite state machine. Remember that this is how our system works. We have inputs coming from the user, and we have the states also going back to our ROM, and that's going to help us decide what we're going to do. That's why, if you remember the control ROM beforehand, it was with 8 outputs. This one's going to require, how many outputs do we need now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 and then 4 for which state? Why do we have 4 for the states? Well, remember back here, we had up to 12, and you're going to need 4 bits because that's up to 16, while 3 bits would have only taken 8 states. So we need 16 bits in order to figure out which state we're in. So basically the current state's going to come in here, and then it's going to activate the diodes on this line to control what goes to each of these muxes or different ALUs and what the next state's going to be. Okay, the first cycle is fetch. What operation needs to be done? The first one, well, we read from it. I have to select the correct program counter in the memory, so that mux is 0. Enable memory to read from the memory, and also enable the instruction register so that we write the result. We should also calculate PC plus 1 since we're not using that circuit right now. So send the PC to ALU, send 1 to the ALU, and select the ALU operation add, and then go ahead and write that back. The next stage is decode. So this is going to look something along these lines, where we want the PC to go here. Oop, do we have? Great. Oh, this is beautiful. So we don't enable the program counter. We do forward it to this mux where we select the program counter as the address to main memory. We enable main memory, we read from it, and we enable the instruction register so the output of this is put into the instruction register. We're not writing to the register file, so we'll disable that. While this is happening, we also forward the program counter over here, send that to the ALU plus 1, which is going through this mux, so these are the selection there. Tell it to do it add, and then store the result into another register called ALU result. So notice we're doing 2 things at once here. We're reading the instruction and we're calculating PC equals PC plus 1. And we don't really care what goes to these muxes because we're disabling the register file. Alright, so on the diode we go ahead and select ones here. Notice that this is going to send us to state 1, aka the next one. Enable that mux, enable the instruction register, and then enable memory, and of course the rest is left for writing. Perfect. So next comes decode, which is state 1 right here. Well, we want it to look something like this because now that we have the ALU result, we want to go ahead and overwrite the program counter, so we need to go ahead and enable that for overwriting. And we have the instruction register, so we need to go ahead and send it to the register file for reading as well as the control to figure out what the instruction is. We don't do anything with memory, we don't write anything to the register file, and then we don't care about the rest. Because this stage, or this cycle, we're figuring out what the instruction is, as well as going ahead and update the program counter while we have the chance. Now this is where the idle nodes are put, because that's what this control logic is supposed to do. It's supposed to take the instruction and then figure out which line we need to jump to. So we'd have basically a wide some type of decoder inside of there in order to decide what our next instruction is. So let's go ahead and say it's an add, aka add state cycle 3 stage 2 or state 2. Well, what's going to happen here? Well, we output the register file to these muxes, get the ALU, and write it to the result. Okay. And then we just disable everything else and then don't care about it because we've disabled everything else. Great. Well, that's easy because then we go to state 3 and you enable that mux and basically disable everything else. We're good to go. State 4 is go ahead and write it. So at state cycle 4, instruction, go ahead and tell us what register we're writing to, and then forward the ALU result to the register file and go ahead and write it. Okay. Enable those, and then disable everything else, and then don't care about everything left over because we're not writing any state there. Perfect. Notice that our next state after state 4 is back to state 0, which will tell us to go back to back to fetching. All right, so what if we're going to do the AND? Well, something similar to fetch and decode. First off, remember fetch and decode to happen just like they do with each one. And the control selects AND. We're going to do something very similar, except for we're going to use the AND operation in the ALU instead of the add. So this basically, these two lines copy paste, and then but instead for the first instruction just state that we're going to do the AND instead of the add, and then of course make sure we go to the correct state afterwards as well. Alright, complete transition function. Ooh. So yeah, you have a state which is 4, and then you would have into that control ROM. What this is picturing over here is this not the control ROM but the control logic. And we're on cycle 2. How do we know which instruction we're going to? Well, the opcode's 3 in this this example. We'll just have a 3-bit opcode just to make things simple for our pictures. Obviously, in our Verilog, the opcode is 6 bits, but we're here only going to have 3. So that would index into a decoder, which will again activate a control ROM, and then that would send it back up there. So the next state would be if you select 0, it's from this decoder. 1 would come from this state, and so if we're on state 2, then we would have the next state choose from 1 because that's telling us what instruction, decoding the instruction to the next state for us. Otherwise, we're always using what's in the control ROM. Okay. So in this case, they've made a bunch of 1s, and that would signify that, hey, look, let's go ahead and select 1 instead of 0 because we all send it to an AND. Perfect. 1 means use the opcode to decide the next instruction. Alright, so we go back to fetch, execute the next instruction. Let's go and look at move L. So notice that this is cycle 3 of move L. Cycle 1 and 2 were used to fetch the instruction decoded, just like with our add and our AND. But now we're going to do the move L. Well, move L, we need to read from that register file, get a sign extend from the instruction, put it to the ALU, get the ALU result, and then disable everything else. And of course, when those are disabled, we don't care about what's in those. Here's a control ROM telling us to go to the next state, as well as with selecting the muxes accordingly. Then cycle 4 is where we actually use the ALU result in order to figure out what address we're going to read from. So there comes the address. We're going to go ahead and read from it. And then we go ahead and disable everything else because we're not using it. And then once those are disabled, we kind of don't care about their inputs. So again, make sure we're going to the next state here. We enable the memory. And then on this cycle, hopefully some of you have noticed that usually with the instruction, with your data memory, everything was outputted as a data register. It was a register inside of memory. And that would go ahead and get forwarded to this mux. And then of course the instructions of which register we're writing to would be forwarded as well to the register file. So we'll have to go ahead and enable this and then disable everything else, and then once those are disabled, we don't care about what happens next. So there we go. And of course, now that the move L instruction is complete, we go ahead and tell it to go back to instruction 0 or state to 0. Move S is going to be a little similar. You can go ahead and follow that if you want to, but namely it's the first, just like the first instruction in move L where you're calculating the address, but then instead of just loading, we write to it, and since we're writing, we don't need another cycle in order to store it to the register file, so it only takes 2 cycles. And then the jump, that's where things get a little confusing. Oops, I forgot to update that from BEQ to JA. You didn't see that. We've done a fetch and decode. Now that we have that, we go ahead and get the sign extend for, in this case, what the address is going to be, which is what we usually send to the JA instruction. So we calculate what that is, send it to the ALU result, because that's where we're jumping to. And then the next one is we write if the data registers were equal to each other beforehand. So you may have to send that to an ALU, which should have saved it off in EAQ from our CMP instruction, and then we'll forward it back to the program counter. I am skipping through this pretty quickly because we are not going to implement multi-cycle in Verilog, but we do need to talk about multi-cycle for the next step of the process that we're going to make any sense. Alright, there we go. Okay, we could do jump and link or CMove. Unfortunately, due to the way CSU has done things this semester, we're going to skip those two instructions. And that is our multi-cycle data path. Alright, and that should be it. Whoops. Alright, and that's actually all for today. I am not assigning any work. I'm sure y'all were going to need at least a day to recover from that wonderful experience last night, or 2 nights ago. And so go ahead and take a breather, but don't forget to jump on your work. I did assign 5 problems last time. Go ahead and get started on that. We've talked about multi-cycle. And then on Monday, we're going to go through the next processor, which we are going to at least implement part of in Verilog in this class. But besides that, go ahead and have a good weekend.